In this video, I want to show you how to change spectrogram settings in Praat. So here I have a sound open in Praat, and I'm going to click on View and Edit, and my editor window pops up with the waveform and the spectrogram. Remember, I can go to Spectrum and click on Show Spectrogram to toggle the spectrogram to appear or not to appear. Let's turn it back on. And the other crucial thing to know about the spectrogram is that its axis in Praat is shown here on the left. So right now the spectrogram is displaying frequencies from 0 Hz to 5,000 Hz. If I click anywhere in the spectrogram, all this left number is going to tell me is where I am in the y-axis. So right now I am located at about 1996 Hertz. I could click anywhere along the sound and it's just going to tell me where I am in the y-axis. So for instance, if I want to know, what's this frequency range where I get all this energy here? As you can see, because it's very dark. So if you look, this is all around 4,400 something Hertz. So that's what all this number, the red number on the left, is telling me. Now, there's a few important settings I want to tell you about for the spectrogram. So if I go to Spectrum and go to Spectrogram Settings, the first one I want to tell you about is the view range. So right now I was telling you we're going from 0 Hz to 5,000 Hz. There are occasions where you might want to change that. For instance, often when we're looking at fricatives and trying to tell fricatives apart and look at their acoustic properties, we want to go up to as high as 7,000 Hz. So if I do that and I hit Apply, Apply allows me to see what happens while keeping this dialog window open. And you can see, look at all that strong energy in here going all the way up into these high frequencies. So now you can see on the left axis that the spectrogram shows from 0 Hz to 7,000 Hz. So that's the view range. Now another setting I want to talk to you about is the dynamic range here. Currently this is set to 50. Yours might be at 70. 70 is the default for Praat. So it is at 50 right now. I'm going to change it to 70, hit Apply, and let's see what happens. Wow, the whole spectrogram became a lot grayer. Now let's go back to 50. So you can see that dropping the dynamic range will essentially whiten the spectrogram. So it's like dropping the overall levels for the grayscale to amplitude levels. Okay, this is actually a very important decision to make before you start segmenting something. What dynamic range are you going to use for the spectrogram? To give you a hint of why this is so important, let's keep an eye. I'm going to highlight or select this region where we have this weak fricative, right? And let's see what happens to it as I adjust the dynamic range. Alright, so now let's turn it up to, let's say, 80 and apply. And you can see that the background levels have become so gray that I can barely tell where the fricative even is. Now let's drop it down to, let's say, 30 and hit Apply. Oops, now it's even disappeared. Only the really strong, the really dark regions where there's a lot of energy, like in these fricatives, is still appearing. But the weaker amplitudes of the f is not showing up. So now if I put it back to 50, you can see that that's a pretty good compromise. I can see where this frequency energy is relative to its surrounding vocalic material. So you can see right away why this would be a real big issue for segmenting. If I was trying to segment out this fricative, if I'm at 30 dB, I can't even see it in the spectrogram. And same thing if I'm at 80 dB, it's so dark, it's kind of hard to tell where it is. So 50 is a pretty good compromise. In general, it depends on your recording what might be the best dynamic range, but generally I find 50 to be pretty good. Okay, so there's this one last setting that's a very important one for spectrograms I want to tell you about, which is the window length here. I'm not going to tell you exactly how it works. That will be for another time, but I just want to show you what happens when I change it. Right now the default setting is at 0.005. Let me change it to 0.05. Let's see what happens when I hit apply. Wow. You can see the sort of smeared out regions over the y-axis have been resolved into these little bands. To see that a little bit better, let me change the view range from 0 to 1000 hertz. So look at these individual bands being resolved. You can see that they follow the shape of the pitch track, and that makes sense because they're the harmonics of F0. So you can see that by taking the window length and increasing it to 0.05, we're able to resolve the individual harmonics here in the spectrogram, corresponding to exactly, if I take, let's say, a spectrogram, or sorry, take a spectral slice over this region, all these, that little comb of evenly spaced peaks, all those harmonics, that's what we're picking up on in those narrow bands that we're showing here. So this comb structure, we're seeing it appear here. Now, if I go back and go to spectrogram settings, and let's return to our original window length. So I hit standards, it will go back to defaults, 0 to 5000, window length of 0.005. Then I'm going to go from the narrowband spectrogram I have right now, apply, to the wideband spectrogram I had before, where I have some smearing out over the frequencies, so I'm not resolving the individual harmonics. So this wideband spectrogram, this is typically what we use when we're segmenting. And that's because there's an inverse relationship between the resolution we have in time and the resolution we have in frequency in the y-axis. So let me zoom in and show you better what I mean. I'm going to zoom to selection here, and using the wideband spectrogram, I can see very precisely where exactly this vocalic material is ending. Right around 1.08861 seconds, in fact. Alright, so now I'm in my wideband spectrogram. Let's change it to a narrowband spectrogram. So now let's change the window length to 0.05. Hit apply. And whoa, okay, so now you can see I resolved the individual harmonics, so I have very high resolution in the frequency, that is in the y-axis. But in the x-axis, how am you can barely really see what's going on here. So you can see that higher frequency resolution, that is in the y-axis, trades off with a lower resolution in time in the x-axis. So this is why we don't segment usually with narrowband spectrograms, but instead with going back to standards with a 0.005, instead we segment with wideband spectrograms. And now we can see again where the segment boundary is.